Press your hand flat against a table and push. It stops. The table holds, your hand holds, and neither one gives way. That firmness goes all the way down to the protons packed into the heart of every atom in your hand and in the wood, and each of those protons, the tiny solid ball we draw in every textbook, is almost entirely empty, filled less with stuff than with energy tied into a knot, behaving in ways that still unsettle the people who study it for a living. This is a story about the inside of the proton. We will build it slowly, one plain step at a time, starting from the atom you already know and working our way down to its deepest layer. If you enjoy taking a single idea apart calmly and completely, consider subscribing and stay with me. So, a simple question to start. What is a proton actually made of? Think about the last heavy thing you carried. A full kettle, a box of books, a sleeping child against your shoulder. It had weight, and that weight pressed down into your arms, and your arms pushed back, and nothing passed through anything. The world is dependable that way. Chairs hold, floors hold. When you knock on a door, your knuckles stop at the wood, and the sound travels on without you. All of that steadiness, every last bit of it, traces back to a particle you have never seen and never will. That particle is the proton. It sits at the center of every atom, and every atom is a building block of everything solid you have ever touched. The wood of the table, the bones in your hand, the water in your glass, the air pressing on your skin, all of it is atoms, and at the heart of every one of those atoms sits at least one proton. Hydrogen, the lightest and most common atom in the universe, is a single proton with a single electron circling it. Everything heavier is a proton count going up one by one. Carbon carries 6, oxygen carries 8, iron carries 26. The number of protons is what makes an element the element it is, and nothing else can change it. So when you press your palm to a wall and it refuses to let you through, you are meeting protons, in a sense, though not in the way you might guess. The wall does not stop you because its protons are hard little stones your hand cannot squeeze past. The stopping is done mostly by the electrons, which repel the electrons in your skin. But the electrons only stay in place, only hold their careful shells and shape the atom at all, because the protons in the middle pull on them. Take the protons away and the whole structure has nothing to gather around. The solidity you feel is electric, and the protons are the anchor that makes the electricity add up. Here is the first strange thing, said plainly. The proton is heavy for something so small. Compared to the electron circling it, the proton weighs about 1,800 times as much. Almost all the weight of ordinary matter, the weight you feel in that box of books, lives in the protons and their close cousins, the neutrons packed into the atomic core. The feather-light electrons contribute almost nothing to the scale reading. When you weigh yourself in the morning, you're very nearly weighing your protons and neutrons and little else. For a long time, that was a comfortable picture. The proton was the solid, positive, dependable center. It carried the charge that held the atom together. It carried the mass that gave matter its heft, and it seemed, from the outside, like exactly the kind of tiny hard ball you would draw if someone asked you to sketch the middle of an atom. A dot with a plus sign. Small, simple, done. That picture is where we begin, because it is the one almost everyone carries, and it is honest as far as it goes. The proton really is the center. It really does carry the charge and the mass. It really is the thing that makes your hand stop at the table. All of that is true, and none of it is the surprise. The surprise is what is inside. When physicists finally found a way to look, really look, into the middle of the proton, the solid ball came apart in their hands, and what replaced it was stranger than anyone drawing that little dot had imagined. Before we can see why, though, we need a feel for how small this thing is, and how much emptiness we're talking about when we say the proton sits at the center of the atom. That emptiness is the next step down. Picture a cathedral. High stone ceiling, long echoing nave, light coming down through the tall windows in slow shafts. Now walk to the very middle of the floor and set down a single grain of salt. That grain, alone in all that space, is roughly the proton, and the cathedral around it is roughly the atom. That is the ratio. The nucleus at the centre of an atom is about 100,000 times smaller than the atom as a whole. Everything else is room. The atom is famous for being small. It is so small that a line of 10 million of them, laid end to end, would stretch about the width of your fingernail. But the proton at its centre is smaller again by a factor that is hard to hold in the mind. If you blew an ordinary atom up to the size of a sports stadium, the nucleus would be a pea somewhere near the centre circle, and the electrons would be specks of dust drifting somewhere up near the highest seats. In between, filling the whole vast bowl, there is nothing. No stuff. Just the electric pull reaching across the gap. This is the part that unsettles people the first time they truly take it in. The solid world is mostly empty. Your hand, the table, the wall, all of it is far more space than substance. If you could remove the emptiness from every atom in a human being and pack the protons and neutrons together with nothing wasted between them, the entire person would shrink to something you could barely see, a speck smaller than a grain of dust, and it would still weigh what the person weighs. The heft stays. Only the room goes away. That actually happens, out in the universe, when a large star dies. The core collapses, the emptiness is crushed out of the atoms, and the protons and electrons are squeezed together so hard they merge into neutrons. What is left is a neutron star, a ball of nuclear matter about the width of a city that carries more mass than the sun. A single sugar cube of it would weigh about as much as a mountain. That density is not exotic magic. It is just what ordinary matter looks like with the empty cathedral taken out. So the proton is tiny, and it holds up a structure vastly larger than itself, mostly across empty space, by reaching out with its charge. The size of the proton, measured across, is about 1/quadrillionth of a metre, written as a fraction that is a 1 sitting under a number with 15 zeros. It is difficult to feel a number like that. Try it this way instead. The proton is smaller compared to you than you are compared to the sun. You could stack a chain of yous from here to the sun and back many times before you match the gap between your size and the protons. And yet this speck is not a smooth, featureless point. That is the thing to hold on to as we go inward. For a long time nobody could see any detail in it, because nothing they had was fine enough to probe something that small. The proton looked like a point simply because our tools were too blunt to see otherwise. A grain of salt seen from across the cathedral looks like a dot too. Walk up close, and it has faces, edges, structure, a whole geometry that was there the entire time. Physics spent the first part of the 20th century learning that the proton was there at all, and giving it a name before anyone could dream of walking up close. That naming came out of glowing tubes and a New Zealander with a very loud voice, and it is where the real story starts. In the 1880s, a German physicist named Eugen Goldstein was working with glass tubes emptied of most of their air, with metal plates inside and a high voltage across them. Run the current, and the thin gas glowed. This was the technology that would later become the neon sign and the old television screen, and in Goldstein's hands it became a tool for discovery. He drilled small holes, or channels, into one of the metal plates, and noticed a faint glow streaming through them, going the opposite way from the more famous cathode rays. He called them canal rays, after the channels they came through, in 1886. Nobody yet knew what they were. It took another dozen years and other hands to work it out. Wilhelm Wien, and later Joseph John Thomson in England, measured how these canal rays bent in electric and magnetic fields, and found they were positively charged and heavy, far heavier than the electron, the lightest and simplest of them. The ones that appeared when the tube held hydrogen gas were the lightest positive particles anyone could make. They were, though no one said it this way yet, bare hydrogen nuclei, bare protons. The man who pulled it all together was Ernest Rutherford. Born on a farm in New Zealand, a big, blunt, cheerful physicist with a voice so loud that colleagues joked it could fog the photographic plates. Rutherford had already shown, a few years earlier, that the atom had a tiny, dense nucleus at its centre by firing particles at gold foil and watching a few bounce almost straight back. He said it was as surprising as firing a shell at tissue paper and having it come back and hit you. Now he turned to the nucleus itself. In experiments finishing around 1919, Rutherford fired fast particles into nitrogen gas and knocked something loose. What came out behaved exactly like the nucleus of hydrogen. He had chipped a piece off the nitrogen nucleus, and the piece was a hydrogen nucleus, which meant hydrogen nuclei were sitting inside other, heavier nuclei as building blocks. That was the clue that this little positive particle was not just the core of hydrogen. It was a shared ingredient, a fundamental brick that every nucleus was partly made of, a brick that basic deserved a name. Around 1920, Rutherford proposed one. He reached back to the Greek word protos, meaning first, and called it the proton. There was a quiet double meaning in the choice. Almost a century earlier, an English chemist named William Prout had guessed that every element might be built from hydrogen, that hydrogen was the primary matter from which all else was assembled. Prout had been dismissed and half forgotten. Rutherford's name gave him a nod. The proton was the first thing, the primary brick, and Prout had not been entirely wrong, so by the early 1920s the proton had a name and a job. It was the positive particle at the centre of the atom, one for hydrogen, more for everything heavier, the carrier of the charge that held the electrons in their orbits. It had a measured mass and a measured charge. It was real, it was countable, and counting it told you which element you had. The chemistry of the whole world reduced to how many protons sat in the middle. What nobody had in 1920 was any sense of the inside. The proton was a fact, but a flat one, a positive dot with a weight. To go further, you would have to ask what it was made of, and for a while there was no reason to think it was made of anything at all. It looked like a single, simple object, and the simplest thing to imagine was a small, solid ball. That picture came next, and it was good enough to believe for decades. Hold a marble in your hand. It is small, it is solid, it has a definite edge, and if you flick another marble at it, the two click and bounce apart in clean straight lines. For a long stretch of the 20th century, that was the honest working picture of the proton. A tiny ball, positively charged, with a definite size and a definite edge, sitting quietly at the centre of the atom. Physicists knew it was small. They knew its mass and its charge. They pictured it as a hard little sphere, and for many questions that picture worked beautifully. It worked because most of the time you do not need to know what a thing is made of to predict how it behaves. A cannonball follows the same arc whether it is solid iron or hollow, as long as you know its weight. Chemistry treated protons this way with great success. Count the protons, count the electrons, and you could predict how atoms would bond, what molecules would form, what a substance would do. The billiard ball proton let chemistry become a precise science. It carried the plus charge, it anchored the electrons, and its inner life, if it had one, never came up. The picture had real virtues, and it is worth honouring them before we watch it fall. A billiard ball proton is definite. It has a location, it has a size, it has a surface. You can imagine holding it, painting it, weighing it in your palm. It is the kind of object the human mind is built to handle, because it is the kind of object our hands evolved to grab. When you draw the atom as a sun with planets, that little central sun is the billiard ball proton, and generations of students learned the atom exactly that way, and were not badly served by it. The proton's charge, in that picture, is spread smoothly over the ball, or bundled at its centre, and it reaches out into the space around it to grip the electrons. Its mass is just the mass of the ball, a fixed number you could look up, the same for every proton everywhere. Two protons are identical the way two ball bearings off the same line are identical, only more so, because at this level there are no scratches, no flaws, no way to tell one from another at all. A proton is a proton is a proton, and each is a perfect little sphere of positive charge, and it is small enough to seem simple. When you cannot see inside a thing, the plainest guess is that there is no inside to see, that it is solid all the way through, the same substance from surface to centre. A cannonball is like that. A marble is close, so why not the proton? Nothing about its behaviour, in the ordinary chemistry of the world, demanded anything more complicated. It pushed and pulled with its charge, it carried its weight, and it did both as if it were a single seamless object. The trouble with a good simple picture is that it invites a harder question, and the hard question here is almost childish. What happens if you look closer? What happens if, instead of flicking gentle marbles at the proton and watching them bounce, you fire something so fast and so fine that it can reach inside, past the surface, into whatever the middle actually is? A marble struck softly just rolls away. A marble struck hard enough might shatter, and in the pieces you would learn whether it was solid or hollow, one thing or many. Nobody could strike the proton that hard until the late 1960s, when a machine 2 miles long built into the ground in California finally gave physicists a hammer fine enough to feel the inside of a proton. When they swung it, the billiard ball did not survive the blow. What they saw instead was the first sign that the proton had parts. In the hills south of San Francisco at Stanford, physicists built a machine 2 miles long. It was a straight line, an accelerator that took electrons and pushed them and pushed them and pushed them until they were moving at very nearly the speed of light, carrying enormous energy in a package smaller than an atom. Then they aimed that beam at a small target of liquid hydrogen, which is to say a target of protons, and watched how the electrons scattered off. This was the late 1960s, and the experiment was run by a team including Jerome Friedman, Henry Kendall and Richard Taylor, careful experimenters who would share a Nobel Prize for what the machine showed them. The idea was an echo of Rutherford's gold foil, scaled up enormously. Rutherford had fired particles at atoms and learned there was a hard nucleus inside, because now and then a particle bounced back sharply instead of sailing through. If the proton were a soft, smooth ball of charge, the fast electron should mostly graze past it, deflected only a little, the way a marble rolled across a smooth pillow barely turns. A gentle target gives gentle scattering. That was the expectation going in. That is not what happened. When the electrons hit the proton hard enough, some of them bounced off at sharp angles, kicking back with a violence that a soft, smooth ball could never produce. It was Rutherford's shock all over again, one level deeper. The electrons were hitting something small and hard inside the proton, glancing off concentrated lumps rather than sinking into a smooth cloud. The proton was not a uniform ball of charge. It had hard grains inside it, points where the electrons could strike and rebound. This kind of experiment earned a careful name: deep inelastic scattering. Deep because the electrons were reaching deep inside, past the surface. Inelastic because the proton did not simply bounce away whole. The collision was violent enough to break it up and shake new particles loose, the way a hard enough hit shatters rather than nudges. By studying exactly how often the electrons scattered at each angle and each energy, the team could read, in the pattern, the presence of small, hard scattering centres buried in the proton's interior. For a while, nobody was sure what those hard centres were. They could have been a mathematical quirk, a feature of the equations rather than real objects. The data showed a striking simplicity, a pattern that stayed the same whether you hit the proton somewhat hard or very hard, and that simplicity was a strong hint. It suggested the proton was built of pieces small enough that each one behaved, during the brief instant of collision, like a free tiny target on its own, rather than part of a connected whole. The electron was not bouncing off the proton, it was bouncing off something inside the proton. That was the crack in the billiard ball. The solid sphere that chemistry had leaned on for decades turned out, when struck hard enough, to be a container with contents. Something was in there, small and hard and more than one, and the smooth surface had been hiding it all along, the way a bag of marbles feels like a single soft lump until you press on it and feel the shapes underneath. The experiment could show that the pieces were there. It could not by itself say what they were, or how many, or how they were arranged, or why they behaved during a collision as if they barely felt each other, even though nothing that hard and that close should be able to float freely. Reading that pattern and turning glancing hits into a picture of what lived inside the proton took a particular kind of mind. It took someone willing to imagine the proton as a swarm and to do the arithmetic of the swarm, that someone was already famous and he was about to give the pieces a name that stuck. Richard Feynman was one of the most inventive physicists of the century and one of the least solemn. He had helped build the atomic bomb as a young man, cracked the safes of his colleagues at Los Alamos for fun, played the bongo drums, and taught physics with a joy that filled lecture halls. He had a gift for stripping a hard problem down to a picture simple enough to draw on a napkin, and when he looked at the strange scattering coming out of Stanford, he drew one. Forget for a moment the details of the equations, Feynman said in effect. Imagine the proton, when it is rushing toward you at nearly the speed of light, as a loose bag of smaller pieces, each carrying some fraction of the proton's total energy, all flying along together. He gave these pieces a plain, deliberately vague name. He called them partons, simply meaning parts of the proton. He did not claim to know what they were. He only insisted that if the proton were made of small, free-moving pieces, the scattering would look exactly the way the Stanford data looked. The power of the parton picture was that it explained the puzzle of the free-floating lumps. When the electron slams into a proton at very high energy, everything happens in an instant so brief that the pieces inside have no time to influence one another. During that frozen moment, each parton is on its own. The electron strikes a single parton and bounces, as if that parton were an isolated speck and the rest of the proton were not there. So the collision reads out the pieces one at a time, and the whole complicated proton reduces in the flash of impact to a crowd of separate targets. This is why the scattering had that striking simplicity, the pattern that barely changed as you hit harder. If the proton were a smooth ball, hitting harder would reach into different depths and change the result. But if it were a bag of point-like partons, then hitting harder just meant striking the same tiny points more sharply, and the shape of the result stayed the same. Feynman's partons turned a strange feature of the data into something almost obvious. The simplicity was the signature of pieces. Feynman was careful at first not to say too much about what the partons were. That caution was wise because the parton was a role, not yet a face. Anything small and point-like inside the proton would play the part. The picture worked whether the pieces were particles nobody had named yet, or particles some theorists had already proposed for entirely different reasons. Feynman gave physics a way to talk about the inside of the proton as a population, a set of pieces each carrying a share of the whole, without having to commit to their deeper identity. And that population turned out to be richer than 3 neat lumps. When physicists added up the energy carried by all the partons the electrons were striking, the charged pieces did not account for everything. About half of the proton's momentum was being carried by something the electron beam could not see at all, something with no electric charge, invisible to a probe that works by electric push and pull. Half the proton was missing from the picture, hidden in pieces that did not answer to electricity. That missing half would turn out to matter enormously, and we will come back to it. But the charged partons, the ones the electrons could strike, were the ones that had faces waiting for them. A few years before Stanford ever ran, 2 theorists had already predicted from a completely different direction that the proton should be built of exactly this kind of piece. They had not been thinking about scattering at all. They had been staring at a wall of particles looking for a hidden pattern, and the pattern had told them the proton had 3 pieces inside. Those pieces would come to be called quarks. By the early 1960s, physics had a problem that felt less like discovery and more like a flood. Machines called particle accelerators, smashing beams together at higher and higher energies, kept producing new particles, dozens and then hundreds of them, each one slightly different, each one seeming to demand its own place in the catalogue. What was meant to be a short list of fundamental building blocks had swollen into a zoo. Physicists took to calling it exactly that, the particle zoo, and the joke carried an edge of despair. A list that long is not an answer. It is a question you have not solved yet. Murray Gell-Mann was the kind of physicist who solved that kind of question. He was a prodigy, restless, and famously wide-ranging, as at home with linguistics and bird-watching as with equations, and he had an ear for hidden order. Looking at the sprawling zoo, he noticed that the particles were not random. If you sorted them by their properties and laid them out, they fell into neat geometric patterns, tidy hexagons and triangles, with the particles landing at regular points like beads on a lattice. There was a symmetry underneath the chaos. Gell-Mann, with a wry nod to a Buddhist teaching, called it the Eightfold Way, and the physicist Yuval Ne'eman arrived at much the same picture independently. A pattern that clean is a clue, the way the repeating columns of the periodic table were once a clue that atoms had inner structure. The Eightfold Way worked so well that it even predicted a particle nobody had seen yet, a gap in the pattern where a new particle had to sit. When that particle, the omega minus, was found, right where the symmetry said it would be, the pattern stopped looking like a coincidence and started looking like a law. Gell-Mann asked the deeper question. What would have to be true underneath for these patterns to appear at all? And he found that every one of them could be built from just a few basic pieces, combined in different ways, the way every word on a page is built from a small alphabet. 3 pieces, in 3 varieties, could generate the entire zoo. He gave them a strange, playful name, borrowed from a line in a James Joyce novel that reads, 3 quarks for muster mark. He called them quarks. At almost the same moment, working at the CERN laboratory in Europe, a young physicist named George Zweig reached the very same idea on his own. He pictured the basic pieces as fundamental cards in a deck and called them aces. Zweig's version was in some ways more concrete, more insistent that the pieces were real objects and not just bookkeeping. But the name that stuck was Gell-Mann's, and quark is what we have called them ever since. Zweig, for his part, later left particle physics almost entirely and turned to studying how the ear hears, a second career in the science of hearing. The idea was radical, and even its authors were cautious. The quarks had a property that made them hard to swallow. Every particle anyone had ever measured carried a charge that was a whole multiple of the electron's charge, or 0. Quarks did not. To build the patterns, the quarks had to carry fractions of the basic charge, 2/3 of it, or 1/3 of it, values no one had ever seen in a free particle. A thing with 1/3 of a charge was, at the time, almost a contradiction. It was easy to treat quarks as a useful fiction, a mathematical trick that made the patterns come out right, without believing that anything so strange really sat inside matter. Then Stanford fired electrons into protons and found hard, point-like pieces inside, 3 of them carrying charge, behaving during the collision as if they floated freely. The useful fiction and the hard, scattering lumps were the same thing. The quarks were real, and it was time to build a proton out of them. The proton, it turned out, is made of 3 quarks, and to see how they fit, you only have to add up their charges. Quarks come in several types, which physicists whimsically call flavors, and 2 of those flavors do the work of building ordinary matter. One is the up quark, which carries a charge of positive 2/3. The other is the down quark, which carries a charge of negative 1/3. These fractions, the very thing that made quarks so hard to believe, are exactly what make the proton come out right. Take 2 up quarks and 1 down quark, add their charges, 2/3 plus 2/3 plus negative 1/3. The 2 up quarks give a total of 4/3. Subtract the 1/3 from the down quark, and you are left with exactly 1. 1 full unit of positive charge, the precise charge of the proton, built out of 3 fractional pieces that could never carry a whole charge on their own. 2 ups and a down, and the arithmetic lands perfectly on the number the proton was always measured to have. Change the recipe slightly and you get the proton's partner. Take 1 up quark and 2 down quarks instead. 2/3 minus 1/3 minus 1/3. That comes to 0. A particle with no charge at all, and this is the neutron, the proton's neutral twin that sits alongside it, in every nucleus heavier than hydrogen. The proton and the neutron are nearly the same weight and nearly the same size, and now you can see why. They are the same 3-quark structure with one flavour swapped. Turn a down into an up, and a neutron becomes a proton. Turn an up into a down, and a proton becomes a neutron. Matter runs on that single small change. The fractions do more than add up. They explain a fact so basic it is easy to overlook, which is that the proton's positive charge and the electron's negative charge match with perfect exactness. Atoms are neutral. The pull of the nucleus and the push of the electrons cancel to nothing, or chemistry as we know it would fall apart. For that cancellation to be exact, the proton's charge must be precisely equal and opposite to the electrons, and the fractional quark charges deliver that. 2/3 and 1/3 combining to give a whole that matches the electron to as many decimal places as anyone has ever checked. So the 3 quarks give the proton its identity. They set its charge at +1. Their flavours, 2 up and 1 down, are the recipe that makes a proton and not a neutron or anything else. If you had asked a physicist in the early 1970s what the proton is made of, this is the answer they would have given, and it is the answer that still appears first in every textbook. A proton is 2 up quarks and a down quark. 3 pieces, and the accounting closes. It is a satisfying picture, as far as it goes, and much of it holds up. The 3 quarks are really there. The charges really do add this way. But a quiet problem sits underneath the neat arithmetic, and it grows louder the moment you ask a simple follow-up. Each of these quarks carries positive or negative charge, and 2 of them, the up quarks, carry the same sign. Like charges push apart. Put 2 positive things close together, and they fly away from each other, harder and harder the closer they get. Yet here are 2 up quarks, pinned together inside a space a quadrillionth of a metre across, not flying apart at all. Something is holding them there, against a push that should tear them loose in an instant. Whatever that something is, it must be strong, far stronger than the electric force it overcomes, and it does not appear anywhere in the everyday world. To keep 3 quarks in a bag that small, physics needed a new force and a new kind of charge for it to grip. Bring 2 magnets together the wrong way and you can feel it in your hands. The closer you push them, the harder they shove back, a firm invisible spring that only stiffens as the gap shrinks. That is the electric and magnetic push between like charges, and it is not gentle. Now shrink the scene down into the proton, where 2 up quarks, both positively charged, sit a quadrillionth of a metre apart. At that range, the electric push between them is ferocious. It should fling them apart violently, in far less than the blink of an eye. And yet the proton sits there, stable, holding its quarks together, apparently forever. So there must be another force at work inside the proton, one that does not merely match the electric push but overwhelms it. It has to be stronger, much stronger, strong enough that against it the fierce electric repulsion of the quarks is a minor correction. Physicists gave this force a name as plain as its job. They called it the strong force, or the strong interaction, and it is one of the 4 fundamental forces of nature, alongside gravity, the electric and magnetic force, and the weak force that governs certain kinds of radioactive decay. Of those 4, the strong force is the most powerful by far, and also the most hidden. Gravity you feel every moment, holding you to the floor. The electric force runs every wire and every chemical bond in your body. Even the weak force shows itself in the ticking of radioactive atoms. The strong force does none of this out in the open. It is so short-ranged that it reaches only across distances near the size of the proton itself, and no farther. Step back even a little, and it vanishes completely. It is a giant confined to a tiny room, immensely powerful within the proton, and utterly absent a hair's breadth outside it. That short reach is why the strong force stayed hidden for so long, and why it feels so strange. Every force we grow up with weakens smoothly as things move apart. Gravity fades with distance. The electric force fades with distance. Our intuition says that is simply what forces do. The strong force breaks that expectation. Inside its tiny room it is overwhelming, and beyond the walls of that room it is nothing. There is no gentle fading tail reaching out into the world. The force that holds the proton together does not touch the next proton over, except through leftovers we will come to later. For the strong force to grip the quarks, though, the quarks needed something for it to grab. Every force works through a charge. Gravity pulls on mass. The electric force pulls on electric charge. If there is a strong force pulling quarks together, then the quarks must carry some new kind of charge, a strong force charge, different from the electric charge they already have. And this new charge could not be the same electric charge, because the electric charge was already accounted for, already pushing the quarks apart. Something else had to be there, a second label on each quark that the strong force could see and act on. This new charge would have to behave differently from electric charge in one crucial way. Electric charge comes in two kinds, positive and negative, plus and minus, and that is the whole story. But the way quarks combine, three of them bound together in a proton, hinted that the strong charge came in more than two kinds. Whatever it was, it had to let three quarks lock together into a stable, balanced whole, in a way that two plus and minus options could never manage. Naming that new charge, and working out its odd threefold arithmetic, gave physics its deepest theory of matter, and it began with a borrowed word from the world of light and colour. The new charge that quarks carry has nothing to do with colour as your eyes know it, but physicists borrowed the word anyway, and once you see why, the name is hard to improve on. Electric charge comes in two kinds, and we call them plus and minus. The strong charge comes in three kinds, and calling them plus, minus, and something else gets clumsy fast. So physicists reached for a familiar set of three that everyone already knows combines into something balanced and plain. They called the three strong charges red, green, and blue. No quark is actually coloured. A quark is far too small to have a colour in the ordinary sense, smaller than any wavelength of light. The names are labels, chosen because of a lucky match. In light, red, green, and blue are the three colours that blend into white, into no colour at all, into balance. And in the proton, the three quarks carry one strong charge each, one red, one green, one blue, and together they add up to a balanced, neutral whole, a state physicists call colourless or white. The everyday fact that three colours of light make white became a perfect handle for the three-part arithmetic of the strong charge. This is the heart of it. A proton is colourless overall, the way white light is colourless, even though it is built from three quarks that each carry a strong charge. The strong force insists on this balance. It will only allow quarks to gather in combinations that come out colourless. Three quarks, one of each colour, make a balanced white proton. That is why the proton has exactly three quarks, and not 2 or 5. 3 is the number that lets the three colours cancel into balance, the way 1 plus and 1 minus cancel for electric charge. The full theory built on this idea has a name that spells out its parts. It is called quantum chromodynamics, and the middle word, chromo, is simply the Greek for colour. Quantum chromodynamics, often shortened to QCD, is the theory of the strong force, the rulebook for how colour charge behaves and how quarks are bound. It stands beside the theory of the electric force as one of the two great pillars describing how the pieces of matter interact. Where the electric theory has one kind of charge in two signs, the colour theory has one kind of charge in three colours, and that extra richness makes it far stranger and far stronger. The idea that quarks carry a hidden three-valued charge did not arrive all at once. It grew from a puzzle. Some particles seem to demand three identical quarks in the same state, packed together in a way that the deepest rules of quantum physics forbid, because two identical particles of that kind are not allowed to share a state. the physicist Oscar Greenberg, and soon after Mu Young-han working with Yoichiro Nambu saw a way out. If each quark carried a new hidden label, a new charge with 3 settings, then the quarks were not truly identical after all. The forbidden crowding was allowed because colour told the quarks apart, so colour solved 2 problems at once. It gave the strong force a charge to grip, explaining what holds the like-charged quarks together against their electric push. And it explained why quarks gather in threes and why the proton comes out exactly as it does. But a force needs more than a charge. The electric force acts by passing something back and forth between charges, a carrier that ferries the push and pull across the gap. The strong force must have its carrier too, a particle that shuttles colour between the quarks and binds them. That carrier is the glue of the proton, and it was found not by imagining it, but by seeing its tracks fly out of a collision in Germany. The electric force works by exchange. When 2 electric charges push or pull on each other, they do it by tossing particles of light back and forth between them, particles called photons. The photon is the messenger of the electric force, the thing that carries the push across the empty gap. Every force in this deep picture of nature works this way, through a messenger particle passed between the things that feel the force. So if the strong force binds quarks by their colour charge, it too must have a messenger, a particle that carries colour from one quark to another and glues them together. That messenger is called the gluon, and the name is honest about its job. Gluons are the glue of the proton. They stream constantly between the quarks, carrying colour charge back and forth, and it is this endless exchange that holds the quarks bound inside their tiny room. If you could freeze a proton and look inside, you would not see 3 quarks sitting quietly. You would see 3 quarks in a blur of gluons flying between them, a storm of exchange far busier than the calm 3-piece picture suggests. Gluons differ from the photon in a way that makes the strong force fierce. The photon carries the electric force, but the photon itself has no electric charge. Light does not shine on other light. 2 beams pass through each other untouched. The gluon is not so aloof. The gluon carries colour charge itself, which means gluons pull on other gluons. The glue sticks to itself. This single fact, that the messenger of the strong force also feels the strong force, is what makes the strong force so much wilder than the electric one, and it will drive nearly everything strange that follows. For years, the gluon was a prediction, a particle the theory required but no one had seen. Seeing it directly was impossible, because a gluon, like a quark, can never be pulled out into the open on its own. But there was an indirect way. When you smash particles together hard enough, the quarks and gluons knocked loose do not fly out bare. Each one dresses itself, on the way out, into a tight, narrow spray of ordinary particles, a jet pointing in the direction the original piece flew. Count the jets, and you count the pieces that were knocked loose. If a collision knocked loose only a quark and an antiquark, you would see 2 jets, flying back to back. But if one of those pieces radiated a gluon on its way out, a hard gluon flying off at an angle, then there would be 3 jets instead of 2. The third one marking the path of the gluon. 3 jets, spraying out in a clear 3-pronged pattern, would be the gluon's signature, its footprint in the debris. In 1979, at a laboratory called DSY in Hamburg, Germany, a collider named Petra smashed electrons into their antimatter partners at high energy, and there in the debris were the 3 jet events, clear and repeatable, seen by several experimental teams at once. The third jet was the gluon made visible, not the particle itself, but the unmistakable track of it flying free for the instant before it dressed itself in a spray. The glue of the proton had left its footprint, and the strong force now had all its pieces, quarks carrying colour and gluons carrying it between them. With the cast complete, the deepest puzzle of the strong force could finally be faced directly. You can knock a quark hard enough to make a jet, but you can never catch the quark itself. Pull on a quark and something stops you, every time, no matter how hard you pull. The reason is stranger than a simple, strong grip. and it comes down to what happens when you try to stretch the glue. Nobody has ever held a single quark. Nobody ever will. You can find quarks inside protons, inside neutrons, inside a whole family of particles, always locked together in colourless groups, but never one alone, out in the open, free to be caught and measured on its own. This is not for lack of trying. It is a rule of nature, and it has a name. Physicists call it confinement, and it is one of the strangest features of the strong force. To feel why, imagine trying to pull one quark out of a proton. You grab it somehow, and you pull. With any ordinary force, pulling two things apart gets easier as they separate, because the force between them fades with distance. Stretch a magnet away from the fridge and past a certain point it lets go. The strong force does the opposite. As you pull the quark away, the force holding it back does not fade. It stays strong, and in a sense it grows, as if the quark were tied to its neighbours by a band that pulls harder the more you stretch it. The reason traces back to the gluons sticking to themselves. Between two quarks, the gluons do not spread out thin and wide the way an electric field does. They pull themselves into a tight, narrow tube, a taut string of strong force energy running straight from one quark to the other. Pull the quarks apart, and you do not weaken this string. You stretch it, and stretching it pours energy into it, more and more at a steady rate. The way stretching a real elastic band stores more tension the farther you pull. Here is where the everyday picture of a string finally breaks, and the break is the whole point. Stretch a real elastic band far enough and it snaps, and you are left holding two loose ends. Stretch the strong force string far enough and it snaps too, but you're never left with a bare quark on each end. The energy you poured into the string at the moment it breaks is so great that it does something matter does all the time given enough energy. It turns into new particles. A fresh quark and antiquark appear out of that stored energy, one at each broken end, and instead of a free quark you now have two colourless particles where you had one. Try to isolate a quark and you make more particles instead. This is why every collision that knocks a quark loose produces a jet, a spray of ordinary particles, rather than a lone quark flying free. The quark tries to leave, the string stretches, the string snaps into new quarks and antiquarks, and they all dress up together into a jet. The quark you tried to free is always in there somewhere, but it is always wrapped in company, never naked. The harder you pull, the more energy you pour in, and the more particles you make. You cannot win. So confinement is not a matter of the quark simply being held very tightly, the way a bolt is held by a strong clamp. It is deeper than that. The very act of trying to separate them creates the conditions that make separation impossible, because the energy of pulling turns into new matter that reseals the bag. A quark alone is not just hard to make, it is something nature will not hand you, no matter the price you're willing to pay. And yet inside the proton, the quarks do not feel tightly clamped at all. Struck by a fast electron, each quark behaved as if it were floating free, barely bound to anything. A quark you cannot pull out is somehow up close, a quark that hardly feels the leash. That contradiction is the next surprise, and resolving it won 3 physicists a Nobel Prize. Here is the puzzle in its sharpest form. Pull a quark away from its neighbours and the strong force fights you harder and harder, until it snaps into new particles rather than let the quark go. That is confinement. But when a fast electron dives into the proton and strikes a quark up close, that same quark behaves as if it were nearly free, floating loose, barely feeling the others at all. That was what the Stanford scattering showed, and it is what let Feynman treat the partons as separate pieces. So which is it? Is the quark gripped in an unbreakable bond, or is it drifting free inside the proton? Somehow, it is both. The answer is that the strong force does something no ordinary force does. It changes strength with distance in the opposite way from what we expect. Up close, when 2 quarks are very near each other, the strong force between them is weak, so weak that each quark drifts almost freely, hardly noticing its neighbours. Far apart, when the quarks are pulled away, the force grows powerful, clamping down, refusing to let go. Near is loose, far is tight. It is the reverse of gravity, the reverse of the electric force, the reverse of nearly everything else in nature. This property has a name. It is called asymptotic freedom, and the plain meaning underneath the phrase is simply this: the closer quarks get, the freer they become. Approach closely enough and they behave almost as if no force acted between them at all. That is why the electron scattering saw free-floating partons. In the instant of a hard, close collision, the struck quark really is nearly free because at that tiny distance the strong force has faded to almost nothing, and it is why the quarks can never escape. Move them apart and the force swells, and the leash only tightens. Asymptotic freedom was worked out in 1973 by three physicists: David Gross and his student Frank Wilczek, working together at Princeton, and independently David Politzer, then a young researcher at Harvard. Each did the difficult calculation and found the same startling result. The equations of the strong force of quantum chromodynamics predicted that the force should weaken at short distances all on its own. It was not put in by hand. It fell out of the theory, once again pointing to the gluons that stick to themselves as the cause. The three shared the Nobel Prize in Physics decades later, in 2004, for showing that the strong force runs backward from our intuition. This backward behaviour is what finally made quantum chromodynamics believable. The theory explained in one stroke two facts that had seemed to contradict each other. The quarks float nearly free inside the proton, which is why the scattering saw sharp point-like pieces, and the quarks can never be pulled out, which is why no one ever catches one alone. Both come from the same rule about the strong force growing with distance. What looked like a paradox was a single deep feature seen from two sides. With asymptotic freedom in place, the theory of the proton's interior was, in its bones, complete. Three quarks, carrying colour, bound by gluons, held by a force that is weak up close and merciless far away. It is a beautiful, closed picture. But it is not the whole proton, not by a long way. So far we have counted three quarks, the ones physicists call the valence quarks, the ones that set the charge and the identity. The real inside of the proton is far more crowded than three. The empty space between the quarks is not empty at all. It boils. We have been counting three quarks, and that count is true in one careful sense and badly wrong in another. Three quarks give the proton its charge and its identity, and physicists call them the valence quarks, borrowing a word from chemistry for the pieces that do the defining work. But if you could look inside the proton at the finest level, you would not find three lonely quarks in an empty bag. You would find them surrounded by a churning crowd, a restless sea of other quarks and antiquarks flickering in and out of existence, never still. This sea comes from the gluons, and from one of the deepest rules of the quantum world: empty space, at the smallest scales, is not truly empty. Energy is always trembling, and where there is enough energy, particles can appear in pairs, a particle and its antimatter partner, born together and vanishing again almost at once. These are called virtual particles, virtual because they live so briefly, borrowing their existence from the energy around them and paying it back before the world can quite take notice. Inside the proton, packed with the enormous energy of the strong force, this flickering runs wild. Every gluon streaming between the quarks can, for a fleeting instant, become a quark and an antiquark, which then find each other and vanish back into a gluon. At any given moment, the proton is full of these fleeting pairs, appearing and disappearing in vast numbers, a constant boil of matter and antimatter that never settles. Physicists call it the quark sea, or the sea quarks, to set them apart from the three valence quarks that persist. The valence quarks are the swimmers who are always there. The sea is the water they swim in, made of countless pairs that rise and fall. This is why, when the electrons at Stanford probed the proton harder and harder, they found more and more pieces to strike. A gentle look sees mostly the 3 valence quarks. A harder, finer look reaches down into the sea and sees the flickering pairs as well. More of them the harder you look, an endless froth revealed in more detail the closer you get. The proton is not a bag with 3 marbles. It is a bag with 3 marbles adrift in boiling water, and the boil is part of what the proton is, not a distraction from it. The sea even contains, fleetingly, quark flavors that the proton has no business carrying. Alongside the up and down quarks that build it, the sea flickers with heavier flavors, strange quarks and heavier still, appearing for the briefest instants before vanishing. They are not part of the proton's identity. They are transients, guests who arrive and leave in the same breath, borrowed from the energy of the strong force and returned before they can be counted as permanent residents. But they are there, and experiments can feel their presence in the way the proton scatters. So the honest inside of the proton is not 3 of anything. It is 3 valence quarks, a vast sea of quark and antiquark pairs boiling in and out, and gluons everywhere binding it all and feeding the boil. The simple 3-quark proton is like a photograph of a waterfall, a still image that captures a shape while hiding the roar and the churn that make the shape exist. The proton is a process caught in the act of holding itself together, and because the sea reveals itself more the harder you look, the proton has a property stranger than any single count can capture. What the proton is made of depends on how you look at it. Look softly, and it is nearly 3 quarks. Look hard, and it is a teeming crowd. The contents change with the sharpness of the question, and that shifting inventory is the next thing to face. Ask what the proton is made of, and the honest answer begins with a question of your own. How hard are you looking? This is not a riddle. It is a real and measurable fact about the proton, and it is one of the strangest things about it. The list of what lives inside a proton is not fixed. It shifts depending on the sharpness of the probe you use to look. A gentle probe and a fierce probe, aimed at the very same proton, come back with different inventories. Look at the proton gently, with a probe that cannot resolve fine detail, and you see something close to the simple picture. 3 quarks, carrying most of the momentum between them, a broad and simple structure, but turn up the energy of your probe, sharpen it so it can resolve smaller distances, and the picture blossoms into crowds. Each of the 3 quarks is revealed to be surrounded by gluons, and each gluon by flickering quark and antiquark pairs, and those in turn by finer structure still. The harder you look, the more pieces you find, and each piece carries a smaller share of the whole. The reason goes back to asymptotic freedom and the boiling sea together. A sharp probe reaches down to very short distances, and at short distances the strong force is weak, so the probe can slip in among the finest flickers of the sea and resolve them one by one. A blunt probe cannot reach that deep, and so it sees the fine structure blurred together into a few broad lumps. It is like looking at a coastline. From far away it is a smooth curve. Look closer and it breaks into bays and headlands. Closer still and every headland is a jumble of rocks, and every rock a scatter of grains. There is no final true number of features. The count depends on the scale of your looking. Physicists capture this in what they call the structure of the proton, described by functions that tell you, for a given sharpness of probe, how the proton's momentum is shared among quarks, antiquarks, and gluons. These are not vague ideas. They are measured precisely, in experiment after experiment, and they change in a predictable way as the probe sharpens, exactly as the theory of the strong force says they must. The way the inventory shifts with scale is itself one of the strongest confirmations that quantum chromodynamics is correct. The changing picture is not confusion. It is a prediction come true. This is why it can be true all at once that the proton is 3 quarks, and that the proton is a seething crowd. Both are correct answers to different questions. 3 quarks is the answer at a soft, broad scale, the scale of the proton's overall identity and charge. A boiling crowd of quarks, antiquarks, and gluons is the answer at a sharp, fine scale, the scale of a hard collision. The proton holds both truths, and which one you meet depends entirely on how you knock. There is a humility in this that is worth sitting with. We're used to a thing being what it is, one fixed set of parts, whether or not anyone is looking. The proton refuses that. Its inner contents are not a settled list waiting to be read, but a living structure whose detail depends on the question. The proton is less like a machine you can open and inventory, and more like a swarm whose number depends on how finely you count. All of this churning, this sea and these gluons and this shifting count, leads to a question that sounds simple and turns out to be the deepest of all. If the proton is mostly boiling energy and flickering pairs, where does its weight come from? The three quarks are astonishingly light. The proton is not. That gap between them is where the real surprise of the proton lives. Weigh a proton and then weigh the three quarks inside it, and the numbers do not come close to matching. This is the fact that, once you truly take it in, changes how you see not only the proton, but your own body and everything around you. The three quarks that make up a proton are extraordinarily light. Add up the mass of two up quarks and one down quark, the mass each one has on its own, and you get about 1% of the proton's total mass. 1%. The quarks that supposedly make the proton account for almost none of its weight. So where does the other 99% come from? It comes from energy, from the furious motion of the quarks racing around inside, and above all from the strong force field, the gluons and the boiling sea, all of it carrying energy, and all of that energy weighing something. The proton's mass is overwhelmingly the mass of the energy bound up inside it, not the mass of the pieces it is made from. The proton is heavy not because its parts are heavy, but because it holds so much energy in so small a space. This works because of the most famous equation in physics, the one that says energy and mass are two forms of the same thing. Energy has mass. A tightly wound spring weighs a shade more than a loose one. A hot object weighs a shade more than a cold one. The effect is far too tiny to notice in a spring or a stove, because everyday energies are small. But inside the proton, the energy of the strong force is enormous compared to the featherweight quarks, and so the energy supplies almost all the weight. When you stand on a scale, the number you read is mostly the energy of the strong force, tied into knots inside your protons and neutrons, weighed as mass. Sit with what that means. The solidity we started with, the weight of the box of books, the heft of your own body, is not the weight of solid stuff at all. It is the weight of bound energy. Strip the energy out and the actual matter, the bare quarks, would weigh almost nothing. Nearly all the mass of everything you have ever lifted, everything you have ever been, is the strong force made heavy, energy caught and held so tightly that it presses down as weight. We are not made of heavy things, we are made of light things bound with tremendous force, and the binding is the mass. This is why the proton cannot honestly be pictured as a little ball of solid substance. There is no dense material at its core doing the weighing. There is a small space filled with racing, flickering, self-binding energy, and that energy is what tips the scale. The proton weighs what it weighs because of what the strong force is doing inside it, moment to moment, holding itself together. Stop the process, and the weight would be gone, because the weight is the process. And yet the quarks do have a little mass of their own, that 1%, small but real. That small mass does not come from the strong force. It comes from somewhere else entirely, from a different field that fills all of space and gives the quarks the tiny weight they carry on their own. That field has a name that reached the front pages of newspapers, and its story is where the proton's mass connects to the deepest layer of physics we have so far reached. The 1% of the proton's mass that the quarks carry on their own has its own strange origin, and it is not the strong force. It comes from a field that fills all of space, the same everywhere, quiet and unnoticed, called the Higgs field. Every point in the universe, the space inside your room and the space between the stars is soaked in it. Most fields are things you can stir up and calm down, strong in one place and absent in another. The Higgs field is different. It sits at a steady value everywhere, always on, and particles moving through it feel a constant drag that shows up as mass. Picture walking through still, deep water. Some things move through it easily, barely slowed. Others, broad and clumsy, feel it drag at them hard. The Higgs field works something like that, except the drag it gives is not a slowing but a weight, a resistance to being pushed around that we measure as the particle's mass. A particle that feels the field strongly as heavy, a particle that barely feels it is light, and a particle that does not feel it at all, like the photon of light, has no mass and flies at the universe's top speed forever. The up and down quarks feel the Higgs field only faintly. That faint touch is where their tiny mass comes from, the small real weight that each quark carries on its own, the 1%. The Higgs field gives the quarks a featherweight, and the strong force does everything else. So the proton's mass has two sources of wildly different size: a sliver from the Higgs, the intrinsic weight of the bare quarks, and the overwhelming remainder from the energy of the strong force binding them. Two mechanisms, one small and one vast, meeting inside a single proton. The Higgs field was proposed in 1964, most famously by Peter Higgs in Scotland, along with several others working at the same time, including François Englert and Robert Brute in Belgium. For almost 50 years it was an idea on paper, needed by the theory but unconfirmed. A field like that should have a particle attached to it, a ripple in the field that a strong enough machine could shake loose, and finding that particle became one of the great hunts in the history of science. It required the largest machine humanity has ever built. That machine is the Large Hadron Collider, a ring 17 miles around, buried beneath the border of France and Switzerland at the CERN laboratory, where beams of protons are whipped nearly to the speed of light and slammed together. In 2012, two enormous experiments there announced that they had found it, the Higgs particle, the ripple in the field, appearing just where the theory said it should. Peter Higgs, by then in his 80s, was in the audience and wiped his eyes. The next year he shared the Nobel Prize with Englert. Brute had died and could not be honoured, as the prize is given only to the living. So the proton's featherweight quarks tie the smallest layer of matter to the field that gives mass across the whole universe, confirmed by the biggest machine we have, and still the strong force does the heavy lifting, supplying that 99%. The Higgs explains why the quarks weigh the little they do. It does not explain the proton's heft. That remains the strong force's doing, energy weighed as mass. We have the proton's mass accounted for now, split between a faint Higgs touch and a vast strong force energy. But mass is only one of the proton's basic properties. It has another, just as fundamental, that seemed for decades like it should be the easy one to explain. The proton spins, and when physicists tried to add up where that spin comes from, the three quarks failed them completely, in a way that set off one of the sharpest crises in the story of the proton. The proton spins. Every proton carries a fixed, unchanging amount of a property physicists call spin, a kind of built-in rotation that never speeds up and never slows down. Spin is not quite the spinning of a top, though the name comes from that image, and the picture is close enough to hold for now. A proton behaves in many ways like a tiny spinning ball of charge, and that spin is one of its defining features, as basic to it as its mass or its charge. It is what makes magnetic resonance imaging possible, the machine in the hospital that reads the spins of protons in your body to build a picture of your insides. Now, the proton is built of three quarks, and quarks carry spin too, the same fixed amount each. So the obvious expectation, once you know the proton is three quarks, is simple. The proton's spin should be the sum of the spins of its three quarks, added up with their directions. Two pointing one way and one pointing the other would leave exactly the proton spin left over. It was so natural an idea that physicists took it nearly for granted. The quarks carry the spin, the way they carry the charge. Add them up and you are done. In the late 1980s, a group at CERN called the European Muon Collaboration set out to confirm this, to measure how much of the proton spin the quarks actually carry. They fired a beam of muons, heavy cousins of the electron, into protons whose spins were lined up in a known direction, and measured how the quarks inside were oriented. It was meant to be a careful confirmation of the obvious, filling in a number everyone expected to come out near 100%. The number came out near 0. The quark spins, added together, accounted for almost none of the proton spin. Not most of it, not half of it, but a small fraction, so small that at first it was consistent with the quarks contributing nothing at all. The pieces that were supposed to carry the whole of the proton spin were barely carrying any of it. The expectation had not been slightly off. It had collapsed. This became known as the proton spin crisis, and the word crisis is not too strong. A property as basic as spin, in a particle as basic as the proton, and physics could not say where it came from. The neat picture, 3 quarks carrying charge and mass and spin alike, had passed every test until this one, and here it failed utterly. The charge added up perfectly. The spin did not add up at all. Something was carrying the proton spin, and it was not mostly the quarks. The result was so surprising that the first response was doubt. Perhaps the measurement was flawed, or the theory of how to read it was incomplete, or the quarks whose spin was measured were only some of them. Physicists checked and rechecked through the following years, with new experiments at CERN, at Stanford again, at the DISI laboratory in Germany. The crisis held. The quarks really do carry only a modest share of the proton spin, later measurements settling on roughly 1/4 to 1/3, still nowhere near the whole. So the proton spin, like its mass, turns out to come mostly from somewhere other than the 3 quarks. The quarks are the identity of the proton, but not its bulk and not its spin. Both of those live largely in the rest of the churning interior, the gluons and the sea and the motion. The question, sharp and unanswered, was where exactly? If the quarks do not carry the spin, then what does? 2 suspects stepped forward. If the 3 quarks carry only 1/4 or 1/3 of the proton spin, then something inside the proton must be carrying the rest. 2 suspects present themselves, and both live in the churning interior we have already met. The first is the gluons. The second is motion itself, the orbiting of the quarks and gluons as they move around inside the proton. Between them, these 2 must make up the large share of spin the quarks fail to provide. The problem is measuring how much each one contributes, because both are far harder to pin down than the quarks. Take the gluons first. Gluons carry spin, just as quarks do, and there are a great many of them streaming through the proton at any moment. If their spins tend to line up with the protons, even a little on average, the sheer number of them could add up to a large share of the total, so the gluons became a prime suspect for the missing spin. But measuring the spin of the gluons is delicate work. Gluons have no electric charge, so the electron and muon beams that read the quark so well slide right past the gluons without touching them. To weigh the gluons' spin, physicists needed a different kind of experiment entirely. The second suspect is subtler, and it is orbital motion. Think of the solar system. The Earth spins on its own axis, and it also travels in a great orbit around the Sun, and those are 2 separate motions, 2 separate stores of turning. The same division holds inside the proton. Each quark and each gluon has its own spin, its own private rotation, but it may also be circling within the proton, carrying orbital motion the way a planet carries it around the Sun. That orbital circling is a form of the same underlying quantity as spin, and it can hold a share of the proton's total turning without any of the pieces having to spin on their own axes at all. This orbital motion is the hardest piece to measure of all, because it is not a property you can read off a single struck quark. It lives in how the quarks and gluons are arranged and moving together, in the shape and swirl of the whole interior. For a long time it was almost a placeholder, the term in the accounting that had to be there to make the books balance, but that no one could measure directly. If the quarks carry 1/3 and the gluons carry some share, then whatever is left must be orbital motion, and for years that was the only way to guess at it, by subtraction. So the full accounting of the proton spin has 4 parts, and it is worth laying them out plainly. The spin of the quarks, now measured, a modest third or so. The spin of the gluons, suspected to be large but hard to reach. The orbital motion of the quarks, and the orbital motion of the gluons, both of them subtle and long, out of reach of direct measurement. Add all 4 together, with their directions, and they must sum to exactly the proton's fixed spin, no more and no less. The total is known with great precision. It is the shares that are hard. This is a very different situation from the charge, where 3 simple fractions added cleanly to 1. Spin does not divide so neatly, because it is spread across the whole restless interior, carried partly by pieces and partly by motion, some of it in forms that resist measurement. To make progress, physicists had to find a way to weigh at least one of the hidden shares directly. The gluons were the first target, and reaching them took a machine designed to collide not electrons, but protons whose spins were themselves lined up at a laboratory on Long Island. To weigh the spin the gluons carry, you cannot use an electron beam, because the gluons ignore it. You need a probe that feels the strong force directly, something that will collide with gluons and come away marked by the encounter. The answer physicists reached was to collide protons with protons, but not ordinary protons. Both beams had to be spin polarized, meaning the protons in them had their spins lined up in a chosen direction, so that the experiment could compare what happened when the spins were aligned against when they were opposed, and read the gluons' contribution out of the difference. Building a machine that accelerates protons while keeping their delicate spins lined up is a formidable task. Protons whipped around a ring tend to have their spins knocked askew by the very magnets that steer them. The machine that managed it is the Relativistic Heavy Ion Collider, known as RHIC, at Brookhaven National Laboratory on Long Island in New York. It is a ring several miles around, and for part of its life it was turned into the world's only collider of spin-polarized protons, threading the beams through special magnets that preserve the spin alignment all the way to the collision. When 2 protons collide with their spins aligned, and a gluon from one strikes a gluon or a quark from the other, the outcome depends slightly on whether the gluon's spins were pointing with the proton's spin or against it. By colliding many millions of times, with the beam spins set sometimes aligned and sometimes opposed, and counting the sprays of particles that came out, the experiments at Brookhaven could tease out how much the gluon's spins tended to line up with the protons. It was a slow accumulation, a signal drawn out of enormous numbers of collisions over years of running. The answer, when it came, was that the gluons do carry a real share of the proton spin, not negligible, comparable in size to the share carried by the quarks. The measurements, refined through the 2010s, found the gluon's spin contribution to be significant and pointing the same way as the protons, enough to close a meaningful part of the gap the quarks had left. It was the first time one of the hidden shares of the proton spin had been weighed directly rather than guessed at by subtraction, and it turned the orbital term from the whole of the mystery into a smaller remaining piece. Even so, the quarks and gluons together, spin for spin, still do not quite reach the proton's full total. A share remains, and by everything measured so far, that share must live in orbital motion, in the circling of the quarks and gluons within the proton. That piece is still being pursued, in ongoing analysis and in experiments yet to run. The Spin of the Proton, decades after the crisis broke, is a book with most of its chapters written but the last one still open. The quarks, the gluons, and the orbits are all in there, and the sum is fixed, but the exact bookkeeping is not yet finished. What the spin story shows, more than any single number, is how far the proton is from the simple ball we started with. Even its rotation is a shared, distributed thing, spread across pieces and motions, no single part of it carrying the whole. And spin is only one of the puzzles the modern proton has thrown at physics. There is another, more basic still, one that sounds like it should have a single obvious answer, and for a decade stubbornly had 2. How wide is a proton? How wide is a proton? It sounds like a question with one plain answer, a number you look up and trust, the way you would look up the width of a coin. And for a long time it was. Physicists had measured the proton's radius, the distance from its centre out to the edge of its smear of charge, and settled on a value they were confident in. Then, around 2010, a new and far more precise way of measuring it gave a different answer, and the two numbers refused to agree. For most of a decade, the proton had two sizes, and no one could say which was right. The proton has no hard edge, so its size means the spread of its charge, how far out the positive charge reaches before it fades away. The older measurements found that spread two ways. One was to fire electrons at protons and see how they scattered, reading the size from the pattern of deflection, the same deep tradition that began at Stanford. The other was to study ordinary hydrogen, a single proton with a single electron, and measure the light the atom gives off with great precision. The electron's orbit dips slightly into the proton's charge, and that dip shifts the atom's light by a tiny amount that depends on the proton's size. Both methods agreed and gave a radius of about 0.8 of a quadrillionth of a meter. Then a team decided to measure the same thing with a cleverer version of hydrogen. Instead of an ordinary electron circling the proton, they used a muon, the electron's heavy cousin, 200 times more massive. A muon circles far closer to the proton than an electron does, so it dips much more deeply into the proton's charge, and the shift in the atom's light is hugely magnified, making the proton's size far easier to read precisely. This monic hydrogen, a proton orbited by a muon, promised the sharpest measurement of the proton's radius ever made. The experiment was carried out at the Paul Scherrer Institute in Switzerland and led for years by the physicist Randolph Pohl. Making monic hydrogen at all is difficult, because the muon lives for only about 2/millionths of a second before it decays, so everything must happen fast. The team caught the muons, formed the strange atoms and hit them with laser light tuned to read the shift, and in 2010 they published their result. It was the most precise measurement of the proton's radius ever made, and it was smaller than the accepted value by about 4%. 4% sounds small, but the new measurement was so precise that the gap was enormous compared to its error bars. The proton could not comfortably be both sizes. Either the old electron-based measurements were subtly wrong, in a way no one could find, or the muon experiment was, or, most excitingly, the muon and the electron were somehow feeling the proton differently, which would have meant new physics beyond everything known. That last possibility is what set pulses racing. It hinted that the two cousins, electron and muon, might not obey exactly the same rules, which would have cracked open the standard picture of physics. So the proton radius puzzle was not merely a bookkeeping disagreement. It carried the scent of something deeper, a possible sign that the universe treated two of its particles differently than the theory allowed. For a decade, physicists did not know whether they were looking at a mistake in a hard measurement or a doorway to new physics. Living inside that uncertainty, not knowing which of two numbers describe the very proton in every atom of your body, is its own strange chapter, and it is worth sitting in that decade before we see how it closed. For most of the 2010s, the proton had two sizes, and physics had to hold both at once. This is an uncomfortable state, and it is worth staying in it for a moment because it shows how science actually feels from the inside, far from the tidy certainty of a finished textbook. Two careful measurements, each trusted, each done by serious people, gave two answers that could not both be true. There was no way to wave the disagreement away. Somebody was missing something, and nobody could find what. The stakes felt high because of what the disagreement might mean. If the muon really felt a smaller proton than the electron did, then the electron and the muon were not interchangeable in the way the theory demanded. The two particles are supposed to be identical in every way but their mass, obeying the same forces with the same strengths. A proton that looked different to each of them would break that rule, and breaking that rule would have been a crack in the foundations, the first hard sign in decades of physics beyond the known. So the radius puzzle drew intense attention. far more than a mere measurement of size would normally deserve. It might have been a keyhole into a larger room. At the same time, the more sober possibility never went away. Measuring the proton's radius by either method is extraordinarily hard. The electron scattering experiments had to extract the size from how the scattering behaved as the collisions became very gentle, an extrapolation toward a limit that is delicate and easy to get slightly wrong. The hydrogen light measurements had to account for a tangle of tiny effects, any one of which, if misestimated, could shift the answer. It was entirely possible that the discrepancy was not new physics at all, but a subtle error buried in one of the hard old measurements, waiting to be found. So physicists lived in the gap. New experiments were designed specifically to settle it. The old hydrogen measurements were revisited with fresh eyes and improved methods. Theorists combed through the analysis of the electron scattering, asking whether the extrapolation to gentle collisions had been done correctly, whether some overlooked effect had crept in. The muon result itself was scrutinized, though it held up under every check. For years the answer stayed genuinely open, and honest physicists would tell you they did not know whether they were staring at a mistake or a revolution. There is a discipline in that patience that is easy to admire and hard to practice. The temptation facing a puzzle that might mean new physics is to leap, to announce that the foundations are cracking. The temptation on the other side is to assume the boring answer, that someone simply erred, and stop looking. Neither leap is science. The work was to keep both possibilities alive, to build the experiments that could tell them apart, and to wait for the data rather than the hope. The proton radius puzzle was a decade-long lesson in holding a question open without forcing it shut. And the question did close, in the end, not with a single dramatic stroke, but with several independent lines of work converging on the same answer. Fresh measurements, done with new techniques and greater care, began to come in, and they did not confirm the crack in the foundations. They pointed instead toward the quieter resolution, the one that kept the electron and the muon identical and put the proton back to a single size. Seeing how that convergence happened, and which of the two old numbers it favoured, is how the puzzle finally came to rest. The proton radius puzzle closed the way real puzzles usually do, not with one triumphant experiment, but with several careful ones leaning the same direction until the weight became undeniable. The turning point came from new measurements of ordinary hydrogen, the everyday kind with an electron, done with better technique than before. A group in Germany, at the Max Planck Institute of Quantum Optics, remeasured the light of hydrogen with fresh precision in 2017, and their result agreed with the small proton the muon had seen, not the larger one the old hydrogen measurements had given. That was the first strong sign that the muon had been right all along, and that the discrepancy lived in the older electron-based numbers rather than in any difference between the two particles. More measurements followed, in hydrogen and in electron scattering both, and the newer and more careful they were, the more they gathered around the smaller value. A scattering experiment at Jefferson Lab in Virginia, called PRAD, measured the proton size by firing electrons at it, with a new design meant to reach gentler collisions than ever before, and it too came back with a smaller radius, matching the muon. So the picture that emerged was that the proton has one size after all, the smaller one, close to 0.8 of a quadrillionth of a metre, but a little less, and that the earlier, larger value had come from subtle difficulties in the old measurements. There was no crack in the foundations. The electron and the muon feel the same proton, exactly as the theory demanded. The muon experiment, far from revealing new physics, had simply been more precise than what came before, and had dragged the accepted number to its true smaller value by being harder to fool. It is worth being honest that this resolution is a little deflating, measured against the hopes the puzzle had raised. For a decade the radius disagreement carried the dream of a doorway into new physics, a first sign of something beyond the known laws. The dream did not come true. What the puzzle delivered instead was a more precise proton radius, and a hard lesson in how difficult these measurements are. That is the ordinary shape of progress. Most anomalies, in the end, are resolved within the existing rules rather than by overturning them, and knowing which anomalies are the real doorways is only possible after the patient work is done. But calling the outcome deflating undersells what was gained. The proton's size is now known far better than it was before the puzzle began, pinned down by Munich hydrogen, by refined ordinary hydrogen, and by a new generation of scattering, all agreeing. A number that had been quietly uncertain and then loudly contested is now one of the well-measured facts about the proton. The decade of disagreement forced physics to sharpen every method it had for asking how wide the proton is, and the sharpening is permanent even though the revolution did not come, and the deeper lesson stays. The proton, this thing at the centre of every atom, was not fully pinned down even in so basic a property as its width, not in this century, not until a long and careful effort settled it. The object is old, but our knowledge of it is still being finished. That unfinished quality runs through the whole modern story of the proton, and it points forward because the most recent experiments are not just measuring the proton's size or spin. They are beginning to map things inside it that no one a generation ago thought could be measured at all. One of those is the pressure. Here is something almost no one expects a proton to have. It has a pressure inside it, an actual mechanical pressure, a push and pull distributed through its interior, the way pressure runs through the air in a tyre or the water in the deep sea. For most of the proton's history, this was not even a question anyone thought to ask, because pressure sounds like a property of gases and fluids and bulk matter, not of a single particle a quadrillionth of a metre across. Yet the proton has one, and in the last several years physicists have begun, remarkably, to measure it. The idea makes sense once you remember what the proton really is. It is not a solid ball, but a churning interior of quarks and gluons, held together by the strong force pulling inward and by the quark's own restless motion pushing outward. Wherever forces push and pull through a volume, there is pressure, a map of how hard the contents press at each point. The proton, being a bound system of forces in tension, must have such a map, a pressure that varies from its centre to its edge. The question was whether anyone could ever measure something so deeply buried. The weigh-in came from a quantity physicists had long studied for other reasons, tied to how the quarks are distributed and how they move within the proton. Buried in that same information, it turned out, was the mechanical structure, the forces and the pressure. To extract it, you need a particular kind of experiment, one that gently probes the proton and reads not just where the quarks are, but how they are being pushed. The experiment of choice fires electrons at protons and catches, among the debris, a specific high-energy particle of light produced in the collision, whose properties carry the buried mechanical information out with them. That process was studied at Jefferson Lab in Virginia, at a machine called the Continuous Electron Beam Accelerator Facility, which sends a steady beam of electrons into targets and measures the results with great care. By collecting many of these gentle collisions and reading the light that came out, a team was able, in 2018, to publish the first look at the pressure distribution inside the proton. It was a landmark, the first time a mechanical property so intimate had been drawn out of a single particle, and it was done by reading patterns in scattering. The same tradition that began with Rutherford and matured at Stanford now turned to a question no one had dreamed of asking at the start. What the measurement showed was a proton with structure to its pressure. Near the centre, the pressure pushes outward, fierce and positive, the quarks and gluons straining to fly apart. Farther out, toward the edge, the pressure turns inward, the strong force pulling the whole thing back together and holding it closed. The proton is a balance of these two, an outward push at its heart wrapped in an inward squeeze at its skin. The two match so exactly that the proton neither bursts nor collapses. It is a particle in perfect mechanical tension, and until recently no one could see that tension at all. These first measurements are rough, and physicists are careful to say so. Reading the pressure inside a proton is at the frontier of what can be done, and the numbers carry real uncertainty, to be sharpened by the experiments still to come, but the outward push at the centre is real, and its scale is staggering when you translate it into terms a person can picture. The pressure at the heart of the proton turns out to rival the most extreme pressures known anywhere in the universe, and that comparison is worth making carefully. The pressure at the centre of the proton is almost impossible to state in a way that lands, because the number is so far outside anything we handle. Physicists estimate the outward push at the proton's core at around 10 to the 35 pascals, which is a 1 followed by 35 zeros in the units we use for the pressure of air and water. There is no everyday comparison that reaches it, so reach instead for the most extreme object in the sky, the one we met early in this story when we squeezed the emptiness out of atoms. The pressure inside the proton is greater than the pressure at the heart of a neutron star. Sit with that. A neutron star is the collapsed core of a dead giant star, a ball of nuclear matter the width of a city holding more mass than the sun, so dense that a sugar cube of it weighs as much as a mountain. It is, by a wide margin, the densest and most crushingly pressurized kind of matter that exists as a stable object anywhere in the universe. And the center of a single proton, the speck at the heart of a single atom of hydrogen, pushes outward harder than that. Every proton in your hand carries in its core a pressure that beats the inside of a collapsed star. This is not because the proton is under some external squeeze. Nothing is pressing on it from outside. The pressure is entirely internal, generated by the strong force and the racing quarks within, a self-made tension that the proton holds against itself. The outward push at the center, straining to blow the proton apart, is matched by the inward pull farther out, the strong force wrapping around and squeezing back. The two are locked in balance so precise that the proton simply sits there, stable, for what may be the entire lifetime of the universe, containing a violence at its heart that dwarfs a dying star and betraying none of it. That containment is the quiet miracle of it. When you hold the proton in your mind as a calm, stable, permanent thing, the anchor of every atom, you're right. But the calm is not emptiness. It is a standoff. It is a ferocious outward pressure and a ferocious inward pull, so evenly matched that from the outside the proton looks perfectly serene. The stillness we began with, the table that holds, the hand that stops, rests on a balance of enormous opposing forces packed into a space too small to imagine, holding each other in check moment after moment without pause. There is something worth carrying in that image. The solid, dependable world is not built on inert, restful stuff. It is built on tension held in balance, on forces so strong they beat the cores of stars, arranged so exactly that they produce stillness. The proton is calm the way a bridge is calm, not because nothing is happening, but because everything that is happening cancels into steadiness. The piece of matter is an achieved peace, a balance of violent things, not the peace of an empty room. And the measurement of that pressure is one of the newest windows we have opened into the proton, barely a few years old, still rough, still being sharpened. It shows how far the story has come from the little billiard ball. We can now ask not only what the proton is made of and how big it is and how it spins, but how hard it pushes against itself from the inside and get an answer. Yet even with pressure mapped, the proton still keeps surprises, and one of the strangest concerns a visitor that has no business being inside it at all, a quark far heavier than the whole proton that seems, somehow, to be part of it. Among the flavours of quark, some are far heavier than others. The up and down quarks that build the proton are the two lightest. Above them sit heavier flavours, and one of them is called the charm quark. The charm quark is heavy, much heavier than the proton it might live inside. This is where it gets strange. The charm quark on its own weighs more than the entire proton, and yet there is evidence that a trace of charm is a genuine, lasting part of what the proton is. A heavy guest somehow folded into a house lighter than itself. At first this sounds impossible, a plain violation of common sense. How can a proton contain a piece heavier than the whole? We are used to the parts of a thing weighing less than the thing itself, adding up to it. But the proton has already broken that expectation once, when we found that its three quarks carry only 1% of its mass and energy supplies the rest. Mass, inside the proton, is not a sum of solid pieces. It is bound up energy, and energy can arrange itself in ways that defy the simple accounting of parts and wholes. A heavy quark inside a lighter proton is strange, but the proton was already stranger than a box of weights. We have to be careful here, because there are two ways a charm quark can appear inside a proton, and only one of them is the real surprise. The first way we have already met. The proton's interior boils with virtual pairs, quarks and antiquarks, flickering in and out of existence, borrowed from the energy of the strong force and paid back at once. Among those fleeting pairs, now and then, a charm quark and a charm antiquark appear together and vanish. This kind of charm is a transient, a guest who arrives and leaves in the same instant, and no one disputes that it happens. It is just part of the boil. The real question is whether there is another kind of charm in the proton, one that is not a fleeting flicker, but a lasting part of the proton's makeup, present as a steady component of what the proton is rather than a momentary borrowing. This lasting kind has a name. It is called intrinsic charm, and it would mean the proton carries, woven permanently into its structure, a trace of a quark far heavier than itself. For decades, intrinsic charm was a prediction argued over but never confirmed, a possibility that some theorists insisted on and others doubted, hanging unresolved. The difference between the two kinds of charm is the difference between a passing thought and a settled trait. The fleeting charm pairs are like a stray idea that crosses your mind and is gone. Intrinsic charm would be a part of the proton's character, always present in some small measure, a genuine ingredient rather than a momentary visitor. Telling the two apart in experiments is extraordinarily hard, because both put charm inside the proton, and you must distinguish a permanent trace from a constant flicker. That difficulty is why the question stayed open so long. The idea that the proton might carry intrinsic charm goes back to the work of the physicist Stanley Brodsky and his colleagues in the 1980s, who argued that the proton structure should include a lasting heavy component, present in the very way the proton is assembled from its pieces. For years it remained contested, a theoretical claim without a clean confirmation. Recently, though, careful analysis of a large body of proton data has found real evidence that intrinsic charm is there, and understanding how a permanent heavy quark can fit inside a lighter proton is worth walking through slowly. To see how a permanent charm quark can live inside a lighter proton, we have to give up one more time the picture of the proton as a fixed set of parts that add up to a whole. That picture has failed us at every turn. The quarks do not add up to the mass, their spins do not add up to the spin, and now their weights do not add up in the simple way either. The proton is better understood as a bundle of possibilities, a thing that exists in many configurations at once. An intrinsic charm lives in that quantum blur rather than in any single snapshot. Quantum physics allows a particle to be in a mixture of states at the same time, not settled into one arrangement but spread across many, each contributing its share to what the particle is. The proton, in this deeper view, is not simply two up quarks and a down quark. It is mostly that, but it is also some small fraction of the time that same trio accompanied by a charm quark and a charm antiquark, folded into the structure. The proton spends most of itself as the light three-quark state, and a little of itself in these more elaborate states, and the average over all of them is what the proton actually is. The energy accounting works because of the same reason the proton's mass is mostly energy. When the proton is momentarily in a state that includes a charm quark and antiquark, the energy for those heavy pieces is drawn from the strong force binding the whole, and the configuration is arranged so the total still comes out to the proton's ordinary mass. The heavy pieces are not stacked on top of the proton's weight, adding to it. They are woven into a state that, all told, weighs what the proton weighs. The blur allows a heavy component to be present without the proton growing heavier, because the proton is the average, not the single heaviest arrangement. Brodsky's insight back in the 1980s was that this heavy component would not be spread randomly. Intrinsic charm, if it exists, should show up carrying a fairly large share of the proton's momentum, the charm quarks moving along with much of the proton's forward motion, rather than drifting slowly in the sea. This gave experiments something specific to look for. Fleeting charm pairs from the boil tend to carry little momentum, but intrinsic charm should appear at high momentum, a heavy quark moving fast in the proton's direction. That distinctive signature was the key to telling the permanent trait from the passing flicker. In 2022, a large international group called the NPDF Collaboration reported that they had found it. By analysing an enormous body of data on how the proton behaves and asking whether the numbers fit better with or without a lasting charm component, they found evidence that intrinsic charm is genuinely present, carrying momentum in just the way Brodsky's picture predicted, at roughly the small level long expected. The heavy guessed is real. The proton does carry, woven into its quantum structure, a permanent trace of a quark heavier than itself. This is perhaps the strangest single fact in the whole story of the proton, and it lands only because everything before it has prepared the ground. A thing that contains a piece heavier than the whole would be nonsense for a billiard ball. For the proton, it is just one more consequence of what the proton has been all along, not a collection of solid parts but a knot of restless energy that can wear many forms at once. That reframing, from a thing to a process, is the truth the whole journey has been circling, and it is time to say it plainly. Step back now and look at what the proton has become over the course of this journey. We began with a little billiard ball, a solid dot of positive charge. Piece by piece that picture came apart. Inside were 3 quarks, then a boiling sea of pairs, then gluons everywhere binding them, then energy supplying almost all the mass, then spin spread across pieces and motions, then a pressure that beats a neutron star, then a heavy guest woven into a quantum blur. No single one of these is the proton. The proton is all of them at once, and more truly, it is what all of them are doing. The deepest way to say it is this: the proton is not a thing, it is a process. It is not a small object sitting still at the centre of the atom, but an ongoing event, a self-sustaining knot of the strong force field that holds itself together moment after moment. The quarks and gluons are not parts you could lay out on a table like the pieces of a watch. They are features of a process that never pauses, a churning that is the proton rather than being contained by it. Stop the churning and there is no proton left because the churning is what the proton is. Think of a whirlpool in a river. A whirlpool has a definite shape, a location, a size. You can point to it and name it and watch it persist for a long time, but a whirlpool is not a thing made of any particular water. It is a pattern in the flow, a way the water is moving, and the water passing through it is never the same water twice. Drain the river and the whirlpool is gone, not because someone removed an object, but because the process stopped. The proton is far more like that whirlpool than like a stone. It is a stable pattern in the strong force field, a shape the energy holds, persisting while everything within it flows. This is why the proton could contain a piece heavier than itself, and why its mass is mostly energy, and why its parts change count depending on how you look. None of these are strange for a process. They're only strange for a thing. A whirlpool can be fed by water from anywhere, can hold more energy than the drops within it, can look simple from far away and intricate up close. Once you see the proton as a self-sustaining pattern, rather than a solid object, its whole catalogue of surprises stops being a list of paradoxes and becomes a single coherent picture. It behaves oddly for a ball because it is not a ball, and this pattern is astonishingly stable. A whirlpool in a river lasts minutes. The proton has lasted since the first seconds after the universe began, roughly 14 billion years ago, and shows no sign of stopping. Whatever else it is, the proton is one of the most durable patterns in nature, a knot the strong force tied at the dawn of everything and has never let slip. The stillness we started with, the table that holds, rests on the permanence of this process, repeated in every proton in every atom, holding its shape across the entire age of the cosmos. But is it truly permanent? A whirlpool ends. A pattern, however stable, is not obviously forever. And so the question arrives that sits under everything. Will the proton last forever? Or does even this most durable of knots eventually come undone? Physics does not fully know the answer, and the not knowing is itself one of the great open questions, watched over in a chamber deep beneath a mountain in Japan. Will the proton last forever? It is a fair question to ask of any pattern, however stable, and for the proton the honest answer is that no one knows. As far as every experiment has ever seen, the proton is perfectly stable. It never decays, never falls apart on its own, never turns into anything lighter. The protons in your body are the same protons that formed in the first minutes of the universe, and they may well outlast the stars. But whether they are truly eternal, or merely so long-lived that we have never caught one dying, is a question physics cannot yet close. The reason the question is open at all comes from the attempt to unify the forces of nature. Physicists have long suspected that the strong force, the weak force, and the electric force, which look so different at everyday energies, are really three faces of a single force that would show itself at enormously high energy. Theories that attempt this unification are called grand unified theories, and many of them share a startling prediction. If the forces truly merge, then the strict rules that now keep the proton stable are not absolute after all, and the proton should be able to decay, extremely rarely, into lighter particles. If those theories are right, a proton would occasionally on its own fall apart, typically into a lighter particle and a burst of energy. The rate would be almost unimaginably slow. The predicted lifetime of the proton in these theories is longer than 10 to the 30-something years, a number so vast that the age of the universe is nothing beside it. You would never see a particular proton decay by watching it, not in a trillion lifetimes of the cosmos. But the rules of the quantum world are statistical, and if you gather enough protons together, a handful should decay each year even if any single one would take eternities. That is the trick behind the search. You cannot watch one proton and wait. Instead, you gather an enormous number of them and watch them all at once. The place this is done most famously is Super Kamiokande, a detector in Japan built deep under a mountain, a vast tank holding 50,000 tons of ultra-pure water, its walls lined with thousands of sensitive light detectors. That much water contains an almost incomprehensible number of protons. If even one of them decays, the flash of particles it produces would light up the sensors, and the vigil would have caught it. For decades now, Super Kamiokande and its predecessors have watched, and they have never seen a proton decay. Not one, clearly, in all that water over all those years. This silence is not a failure. It is a measurement. Every year that passes without a decay pushes the proton's minimum lifetime higher, and the searchers have now established that the proton must live, on average, longer than about 10 to the 34 years, ruling out the simplest versions of the grand unified theories that predicted a faster decay. The theories that survive are the ones predicting decay so slow it is still out of reach. So the question hangs, genuinely open. The proton may be truly eternal, forbidden from ever decaying by an exact law we have not fully recognized. Or it may be merely enormously long-lived, destined to decay on a timescale so vast the universe has barely begun to sample it. We do not know which, and finding out matters, because the answer touches whether matter itself is permanent. The vigil continues, in the deep water under the mountain, watching for a single flash that has not yet come, and while some physicists watch real protons, others have found a way to build one from scratch, inside a computer. There is another way to study the proton, one that needs no accelerator and no underground tank, only enormous computing power and the equations of the strong force. The idea is to build a proton from scratch, inside a computer, starting from nothing but the rules of quantum chromodynamics, and see whether the machine produces a proton with the right mass, the right size, the right properties. If the theory of the strong force is truly correct, then feeding it into a computer and letting it run should conjure a proton that matches the real one. This is one of the sharpest tests physics has of whether it understands the proton at all. The difficulty is that the strong force, up close and inside the proton, is too powerful for the usual methods of calculation. Physicists normally handle forces by treating them as a series of small corrections, each one tinier than the last, adding them up until the answer is precise enough. That approach works beautifully for the electric force, which is weak. It fails completely for the strong force inside the proton, where the force is so strong that the corrections do not shrink and the sum never settles. A different method was needed, one that did not rely on the force being weak. The method is called lattice quantum chromodynamics, and its central idea is to replace smooth, continuous space with a grid. Instead of letting the quarks and gluons roam through a seamless volume, which is impossible to compute, you lay down a fine lattice of points, like the intersections on a vast three-dimensional graph, and you allow the quarks and gluons to exist only on that grid. Space becomes a mesh of closely spaced points, and the equations of the strong force, impossible to solve in smooth space, become an enormous but finite calculation on the grid, something a powerful enough computer can grind through. The computation is staggering in size. Every point on the lattice interacts with its neighbours, the gluons weaving between them, and to capture a proton faithfully the grid must be fine and the volume large, which drives the number of calculations into the range that only the world's most powerful supercomputers can handle. Running these simulations takes months of time on machines built for exactly this kind of relentless number crunching. The quarks and gluons are never watched directly. Instead, the computer samples the countless possible configurations of the field and averages them, letting the proton emerge as the typical shape the strong force settles into. And it works. When physicists compute the mass of the proton this way, starting from nothing but the equations of the strong force and the measured masses of the quarks, the answer comes out matching the real proton's mass within the uncertainties of the calculation. The 99% of the mass that comes from energy, the part no simple picture could explain, emerges naturally from the lattice, produced by the strong force exactly as the theory says. It is one of the great confirmations that quantum chromodynamics really is the correct theory of the proton, that a computer given only the rules builds the proton we actually find. Lattice calculations now reach beyond mass, toward the spin, the pressure, the distribution of charge, computing from first principles the very properties that experiments are struggling to measure. Theory and experiment close in on the proton from two sides, the machines probing the real particle, and the computers building it from the rules, and where they meet is the measure of how well we understand it. They agree remarkably well, and the places where they do not yet agree precisely are exactly where the next generation of experiments is aimed. One of those experiments will be the sharpest proton probe ever built. For all we have learned, the picture of the proton's interior is still blurry in places, and physicists know exactly what kind of machine would sharpen it. It would be a collider, like the ones that reveal the quarks and the gluons, but built specifically to map the inside of the proton in fine detail, to measure how the quarks and gluons are arranged, how they move, how they carry the spin and the pressure and the momentum. That machine is now being built. It is called the electron-ion collider, and it is the future of this story. The electron-ion collider will be built at Brookhaven National Laboratory on Long Island, the same laboratory whose earlier collider weighed the gluon's contribution to the proton spin. It will collide beams of electrons with beams of protons and heavier nuclei, both of them able to be spin-polarized, so that the machine can probe not just where the quarks and gluons are, but how everything inside lines up and moves. It is designed from the ground up to answer the questions this journey has raised, the ones the older machines could only begin to touch, and it is expected to begin taking data in the next decade. What it promises is a kind of three-dimensional map of the proton. The experiments so far have mostly given flat answers, how the proton's momentum is shared, how big it is across. The electron-ion collider aims for depth, a picture of how the quarks and gluons are distributed through the proton's volume and how they move within it, the internal landscape rather than a silhouette. It would let physicists see the orbital motion that holds the last missing share of the spin, map the sea and the gluons in detail, and sharpen the rough first measurements of the pressure into a real chart of the forces inside. Above all, the new collider will chase the gluons, which have always been the hardest part of the proton to see. The gluons carry no electric charge, so they hid from the electron beams that read the quarks so clearly, and everything we know about them has come in directly, painstakingly. The electron-ion collider is designed to probe the gluons far more directly than ever before, to map the glue that makes up so much of the proton's mass and momentum and holds the whole process together. The particle that binds the proton and supplies most of what the proton is would finally be seen in detail. Building it is the work of thousands of physicists across many countries, a project on the scale of years and billions, the kind of long collective effort that the deepest questions now require. No one person will build the proton's map, just as no one person assembled the picture we have walked through here. It came from canal rays and gold foil and 2-mile accelerators and underground tanks and supercomputers, from Rutherford and Feynman and Gell-Mann and hundreds whose names never reach a textbook, each adding a piece. The electron-ion collider is the next chapter of that long-shared labour, and so the story of the proton runs right up to the present and points past it, into experiments not yet finished and answers not yet found. The proton is the oldest and most common piece of matter in the universe, and we are still, right now, learning what it is. That is a strange and wonderful place to have arrived, holding a particle that is everywhere and permanent and still not fully known. It is time to return to where we began, to your hand on the table, and see what all of this has done to that simple, solid moment. Press your hand flat against the table again. It still stops. The table still holds. Nothing about the physics we have walked through changes that simple fact, and that is worth saying plainly, because it would be easy to feel that the solid world has been dissolved by all of this. It has not. The table is exactly as solid as it ever was. What has changed is only your understanding of why, and the why turns out to be far stranger and far more beautiful than the solid picture we started with. So let us answer the title's question in the simplest words. What is happening in the proton's deepest layer, and why does it behave as it should not? The proton behaves strangely because it is not the thing we assumed it was. We assumed a solid ball, and a solid ball should have parts that add up to its weight, a fixed size, a simple spin, no piece heavier than the whole. The proton fails every one of these expectations, not because physics is broken, but because the proton was never a ball. It is a process, a self-sustaining knot of the strong force field, and everything that seemed to misbehave is exactly how a process of that kind should behave. The strangeness was never in the proton, it was in our picture of it. Inside that speck at the centre of every atom, then, is not a tiny stone but a churning balance of enormous forces. 3 quarks that supply the identity and almost none of the weight. A boiling sea of pairs flickering in and out. Gluons everywhere, binding, self-sticking, carrying most of the mass as pure energy. A spin shared across pieces and orbits. A pressure at the core that beats a neutron star. A heavy quark woven in that outweighs the whole. All of it held in a balance so exact that from the outside it looks perfectly, dependably still, and has stayed still since the universe was minutes old. That is what is in your hand. Not solid stuff, but bound energy and tension, repeated in every proton of every atom of every object you have ever touched, including the hand itself. The weight of your body is mostly the energy of the strong force, tied into knots and weighed as mass. The firmness of the table is the electric grip of atoms whose centres are these churning processes. You are made of them, some 10 to the 28th of them, each one a whirlpool in the strong force field, each one holding a violence at its heart and showing you only calm. There is a particular wonder in that, the kind this whole journey has been for. The most common, most ordinary piece of matter in the universe, the proton that sits at the centre of the simplest atom, is one of the strangest and least finished objects we know. It is everywhere, and it is permanent, or nearly so, and we are still building the machines to see what it truly is. The plainest thing in the world, looked at closely enough, opens into something we do not yet fully understand. So the next time you press your hand to a table and feel it hold, you can carry this with you. That firmness reaches down through the atoms to the protons, and each proton is not a little solid ball, but a knot of restless energy beating harder at its centre than the core of a dead star tied at the beginning of time and holding its shape ever since, quietly in you and in everything. The solid world was never solid. It was always this, a still surface over a deep and patient fire, and now, when you knock on the table, you know a little of what answers.